We are going to continue our lectures on stoichiometry with solution stoichiometry. Same reading as yesterday, 275 to 278. And by the end of this lecture, you'll be able to perform calculations and determine the volume or concentration of a reactant or product as opposed to just the mass. And so we saw this slide up in the last lecture, and this was the last lecture. We incorporated the use of our molar mass formula. In this lecture, we're going to be including the use of our concentration formula. And so solution stoichiometry, we need to know it because most chemical reactions involve the use of an aqueous solution because they're easier to handle than solids and gases. And same steps, so we're not really doing anything new. We're just incorporating a formula we already know into the work we already know. So we're going to include our concentration formula, and here's an example. So here we have a reaction for sulfurous acid and potassium hydroxide, and I'm just going to write our formula down up top here. And so these two compounds react, and we want to find the molar concentration of the sulfurous acid solution. So sulfurous acid is H2SO3, and it's aqueous. It's being reacted with potassium hydroxide, so KOH. And again, it's a base, so it's a solution. And they go to produce. Now we can treat this as a neutralization or a double replacement. They both give us the same answer. So K2SO4, that's aqueous, plus water, H2O, liquid. And so there's our chemical reaction. We need to balance it. And I'm taking a look and I've seen two potassiums here, so I'll put a 2 in front of my potassium hydroxide, which means I'll have to put a 2 in front of my water to balance the oxygens. And that gives me 4. I think we're good. I have 4 hydrogens, 2 oxygens on the other side. Oops, this is an SO3. Sorry. SO3, sulfite. And that will keep it balanced. Alright, so now we can put down the stuff that we know. So, we know the volume, 10 milliliters, that's a volume, so 10 milliliters of sulfurous acid. We also know the volume of our base, 15.9 milliliters. And they give us the concentration of the base as well. It's in moles per liter. Anything that's in moles per liter is a concentration. So 1.5 or 0.150 moles per liter. And we're being asked to find the concentration of sulfurous acid. So now we've set up our question. We have a known, we have an unknown, and it looks like we won't even need molar mass for this calculation because we want to find the moles of our known. So the number of moles of KOH, and we can use just our concentration formula. N is equal to concentration times volume. The concentration is 0.150 moles per liter times, and I'm going to convert my volume to liters, so 0.0159 liters, and we get 0 decimal. Sorry there. Some technical difficulty. 0.00 3975 moles. Next, we're going to find the number of moles of our unknown using our mole ratio. So now we can find the number of moles of H2SO3, and that's going to be equal to the number of moles of KOH times our mole ratio of our unknown is H2SO3. Our known is KOH. So we're going to get 0.003975 moles times, and our mole ratio will be 1/2. So we're going to get 0.001987 moles. And now we can find our concentration. So concentration is equal to N over V. The number of moles is 0.001987 moles divided by our volume, 0.01 liters, and we get 0.19875 moles per liter. When we adjust for sig digs, we're allowed 3, so our concentration is going to be 0.200 moles per liter. This is the concentration of H2SO3. And so they work just like the gravimetric stoichiometry. We're just using a different formula to find our moles. Try another example. Here we have a solution of ammonia reacted with phosphoric acid to produce ammonium hydrogen phosphate, which will be used as a fertilizer. And the first thing we got to find is the volume of ammonia needed to completely react 1 kilogram of phosphoric acid with a given concentration, kiloliters as opposed to kilograms. And we want the concentration of ammonium hydrogen phosphate once the reaction is complete. So, first thing we need is a reaction, and we're going to be reacting ammonia. That's a solution of ammonia, so it should say aqueous there. Aqueous plus phosphoric acid, which is H3PO4, and again, aqueous. Going to make ammonium hydrogen phosphate. Now they give us the formula here, but it's one we should be able to get. Hydrogen phosphate is a 2 negative ion. Ammonia is a 1 plus ion. They're both on your table of polyatomic ions on your periodic table. So it is a compound we should be able to make. And so we're going to get NH4 to HPO4 aqueous, and when we go to balance it, even though the hydrogens are the most common, there's 8 hydrogens on this side, there's 6 hydrogens on my reactant side, but because they're in 2 separate compounds, I'm not going to balance them now because I don't know which compound I should put a coefficient in front of. So I'll look at something else. My PO4s are good. I have 1 phosphate ion on each side. On my product side, I have 2 nitrogens. On my reactant side, I only have 1, so I'll put a 2 there. And that will end up balancing everything for me, actually. I now have 2 nitrogens. I have 9 hydrogens on my reactant side. And there's 8 non-hydrogens on the product side. So there's my balanced chemical reaction. And now I'm going to fill in my blanks, as it were, or put in the information I need. So we need a volume of ammonia. So right away they tell us we want to find a volume. They've given us the concentration, so concentration is equal to 14.8 moles per liter. To complete reactant here they give us a volume. It's in kiloliters, so 1.00 kiloliters, and a concentration of 12.9 moles per liter. So again, we have volume and concentration, volume and concentration. It's a good bet we're going to need our concentration formula. And so we're going to use our concentration formula, arrange it for moles to find the number of moles of phosphoric acid. Then again, use our mole ratio to find the moles of ammonia. And finally, we can use our concentration formula to find the volume of ammonia. So, it doesn't hurt to talk to yourself a little bit, get a plan so that you know what order you're going to do things in. So the first thing we need is the moles of phosphoric acid. N is equal to CV. My concentration is 12.9 moles per liter. And because they give me kiloliters, that's the same as 1,000 liters. And so when I multiply them together, it's going to be 12900 moles. And now I can find the number of moles. I'll go up over here. So, number of moles of my unknowns, the number of moles of NH3, which is equal to the number of moles of H2SO3 times my mole ratio, which is moles of NH3 over moles of H3PO4. And so we get 12,900 times 2 over 1, or we end up doubling it, so it's going to be 25,800 moles. So there's the number of moles. We can calculate the concentration now. The concentration of NH3 is going to be equal to N over V, where N is 25,800 moles divided by the volume. Oh, look at that. That's what happens when you go too fast. We want to find the volume. So, we're going to erase this nonsense here, because we're not looking for concentration. We're looking for volume. That's what happens when you go too fast. Okay. So, and volume is equal to N over C, so the volume of ammonia solution is equal to N over C, or moles over concentration, so 25,800 moles divided by the concentration of 14.8 moles per liter. So 25,800 divided by 14.8, and we get 1,743 liters, which is equal to 1.74 kiloliters. And that would be the volume of ammonia. Now the next part of the question is, what's the concentration of our final solution? And here, every time you're asked to calculate a concentration, especially with a final solution, you want to make sure you know what volume you're working with. Or in other words, what volume of this stuff do we actually have? And we're going to go to the next slide to work on this, so we'll be bouncing back and forth a little bit. So we're going to continue example 2. We're looking for the concentration of our product. Before we can find that, we need the volume. Now to get the volume, because we're adding two solutions together, we're adding 1 kiloliter of phosphoric acid and 1.74 kiloliters of my ammonia. So the volume that I'm going to have when I'm done would be the two added together. So my total volume is going to be 2.74. kiloliters, and now I have a chance at answering this question. We know that, and I have to get one more piece of information, so I'm going to go back one more time, and we can use either concentration to help us with our calculation. I'm going to use a concentration of ammonia. We could just as easily use a concentration of phosphoric acid to answer our question. So we know this concentration is 12.9 moles per liter. And so I'll go back one more time just because I keep forgetting my numbers. Alright, and we know the number of moles of ammonia is right here. So NH3. We've done this calculation, so we might as well use it. There's the number of moles of ammonia. From that, we can find the number of moles of ammonium hydrogen phosphate. So the 25800 we're going to use right here. 25800 moles. That's the N. So we already have the number of moles. We don't have to do another calculation for it. We can simply say N of NH4 to HPO4 is equal to the number of moles of ammonia times our mole ratio. Number of moles of NH4 to HPO4 divided by the number of moles of NH3. And so we're going to get our 25800 times, and our mole ratio this time is going to be 1/2. So we're going to divide by 2. So 25800. So we get that 12900. And now we can find our concentration. Concentration is equal to N over V. This is the concentration of NH4 to HPO4, and N is 12,900 moles divided by 2,740 liters. And so our final concentration is going to be 4.7 moles per liter. And there we have it. So sometimes we got to do a little bit of thinking and just using a bit of common sense when we come to our answers. One more example. A sample of silver nitrate solution is reacted with excess sodium sulfate solution. A white precipitate is formed. Calculate the concentration of 100 milliliters of silver nitrate solution if that much precipitate is formed. So we have a reaction. Let's see what we have here. So silver nitrate would be AgNO3, and they said it was a solution, so we write aqueous beside it. It is reacted with the sodium sulfate solution, so Na2SO4, and again they said it was in solution, so it's aqueous, and they react. Now they don't tell us the products, but they do tell us that there's a precipitate, and when we take a look, we have a compound added to a compound. So we're going to do a double replacement reaction. We're going to do Ag2SO4 plus NaNO3. And when we check our solubility table, it turns out that the silver sulfate is a solid. It's a solid, it's not aqueous, whereas sodium nitrate is aqueous. So the silver sulfate is going to be our white precipitate. Precipitate is a solid that's formed in a solution, and so we've found our solid that was formed in the solution, so that's what we're trying to find. We want to find the concentration of silver nitrate solution, so we're looking for a concentration over here. We know that the volume is 100 milliliters, and they gave us a mass of 5.73 grams. And now we're actually going to be using both. Now we have a mass. In order to find the moles of my known, so this is my known, I'm going to need the molar mass. So I can calculate that. What I'm going to find out is I can actually use both my molar mass formula or my concentration formula to find moles or to get out for moles, depending on what I'm being asked for. So I've been given something in grams. I'm going to find the number of moles using my molar mass formula. then my mole ratio, which I should balance my equation for first, and then I can find the concentration using my concentration formula. So first we've got to make sure this is balanced. I need 2 silvers, and I need a 2 in front of my NaNO3, and now we should be good. So first things first, I need a molar mass for silver sulfate. So the molar mass is 311.81 grams per mole. And now I can find the number of moles of my known. So N Ag2SO4 is equal to mass over molar mass, which is equal to 5.73 grams divided by 311.81 grams per mole. And so we end up with 0.0184 moles. Now we can find the number of moles of our known, of our unknown, so the number of moles of AgNO3, and we're going to just shorten this up a little bit. We can write down the number of moles from our last calculation, and we're going to multiply our mole ratio of unknown over known, 2 to 1. That just saves us a bit of pen work. Hopefully it's starting to become second nature, this mole ratio stuff. So 0.0367. 36, we'll write 8. That's the moles. And now we can find our concentration of AgNO3, the thing we're being asked for. Concentration is N over V. 0.0368 moles divided by our volume of 0.1 liters. And we end up with 0.368. And we have 3 sig digs, so we'll go with 368 moles per liter. And I haven't said it before, but I'll say it now. When you're doing these questions, if you're asked to do them on an exam or for an assignment longhand, this would be the minimum amount of work that I would like to see, so I can see all your steps. I for sure, I'll just, with the magic of technology. Alright, so if I was marking this question longhand, I'll show you what I would give marks for. I'd give you 1 mark for having a balanced chemical equation with everything in the right spot and all your states in the right place. This mark is only for the equation. Even if you get the right answer, if you have the wrong equation or if there's something missing, you wouldn't get that mark. So that mark is kind of isolated all by itself. The next thing I'm going to look for is I'll check the right answer. If this answer is right, well, then you're probably good. You're probably going to get 3 marks just for me seeing this. The other mark I like to see is this one. You should always have your mole ratio done, and then you get kind of 1 mark for using the right 2 equations here. So it's a total of 4. Basically what I look for is I look for my balanced chemical equation. If it's there, good. I go and I check to make sure the mole ratio is there. If it is, good. And then I check the answer. If the answer is there, you just got yourself 4 out of 4. If the answer is wrong, then I take a look and see what kind of calculation was wrong. Is it a formula manipulation problem, either this formula or this formula? And if there's only one mistake, then you get 3 out of 4. If they were both wrong, then you're back down to 2 out of 4. And that's how I go through and mark these stoichiometry problems when they're longhand. If they're, say, on the final exam, you'll be asked to do some that are to be worked out. This would be the amount of work I should expect to see, or I would expect to see for a stoichiometry problem. Okay, so homework. There's some practice problems on page 278, and once you've done that, we can go on and talk about stoichiometry involving the ideal gas law. Have fun.